In part 3 of chapter 4, we are going to discuss free body diagramming problems. And before going into the problems, let's see what different types of forces you have learned about. In nature, there are two general types of forces, fundamental and non-fundamental forces. So you're very well aware about the gravitational force, which we are going to study again in chapter 5. Then there are nuclear strong forces that bind the atoms and the molecules in the elements and in our body itself. And there are electroweak forces which act at the nuclear range. Then there are non-fundamental forces. These are not the fundamental forces like friction, tension in the rope, and normal or other support forces. So we are not going to be talking about nuclear forces, chemical energy forces, magnetic forces, or electrical forces here, but our focus in this chapter is going to be on applied forces, support forces, normal forces, tension force, and force of friction, and work on problems related to those. So the success in problem solving is obviously necessary to understand and apply physical principles. Why do we solve problems? And basically we want to understand how things can be calculated, how acceleration can be calculated when force is given, how other parameters can be derived. The basics of problem solving presented before we came into dynamics was that we list out all the variables and we give all the list out all the given quantities and picturize the problem. We are going to follow the same strategy in free body diagramming also, but additionally we have to follow the rules of how to draw a free body diagram for specific strategies. And these techniques also reinforce concepts that are useful in many other areas of physics. Many problem-solving strategies are stated outright in the examples that we'll be solving. And so following step-by-step technique to solve the problems is very much recommended. So we also talk about the gravitational force. We did some problems in the earlier parts, and we talked about weight being the force exerted on an object due to the earth, and we can say weight is either represented by W or also represented by Fg. It really doesn't matter, but normally I used Fg, which is equal to mass times gravity, and it also is a force. Weight is a force, hence its units are Newton. Then there are tension forces that can be created if you tie a rope and then it exerts, it's tugged along. If a rope is tied to the block and you're trying to push it or pull with it, then you know you are applying tension forces. So we will work on problems using the tension force. We normally write it as Ft, and the units are still going to be newtons because it's a force as well. So there can be different scenarios in which tension force can be visualized. This is also an example of tension force, and this is also an example of tension force. Tension forces can be applied horizontally or vertically. So if a rope is passing around a massless, frictionless pulley, the tension will be transmitted to the other end of the rope undiminished. So there's no friction, there's no loss. This has widespread applications. Even in elevator we are using this concept. So when objects are at rest, we say that forces are in equilibrium. When there is zero acceleration, an object is in equilibrium when there is zero acceleration. That means there can be zero acceleration in two scenarios. Object is at rest, or object is moving with constant velocity. If there's a constant velocity, then also we will have zero acceleration. So acceleration can be in horizontal direction, it can also be in the vertical direction. So we will be looking at problems in both these scenarios. So for free body diagramming and problem solving, for example, let's take an example of a box sitting on this floor and a rope trying to pull it down with the help of another mass. So what we do is we draw there's mass 1 and there is mass 2. We draw a free body diagram for this mass and identify how many forces are acting on it. And similarly, we draw a free body diagram for this mass and see what are the forces acting on it. By the way, this is the same rope that is going over the pulley, so this will be force of tension. So it's pulling it in this direction, and the tension force is the same tension force which is pulling on this. It's actually pulling it down, but for us, for mass number 2, the tension is in the upward direction. For mass number 1, the tension is in the horizontal right direction. If there is no friction, then only the force of tension will work in this direction, and there will be normal force on mass number 1 and the weight Fg1 acting on it, because we are talking about mass 1 m1g. Similarly, if I say the free body diagram for number 2 is given as Ft, this Ft is the same, and then there is mass number 2, so m2g is the weight of the mass number 2. So this is how we draw free body diagrams, and if both of them are stationary, nothing is moving, we say net forces for mass number 1, okay, just like you wrote down here. For mass number 1 is 0 in x direction, and net forces for mass number 1 in y direction is 0 because nothing is moving. So this is an equilibrium stage. Same goes for mass number 2. If it's not moving, we can say the net forces for mass number 2, since it's in the y direction, we'll say y2 is equivalent to 0. So net doesn't mean forces are not acting. Net means that sum of all the forces in y direction and x direction in these two scenarios are 0 if there is no motion. So select an object to which the equations of equilibrium are applied. These are the problem solving strategies that you're going to apply, and draw a free body diagram for each object chosen. Include only forces acting on the object, not the forces the object exerts on its environment. We are only concerned about the forces that are acting on the object. Choose a set of x, y axes for each object and resolve the forces into free body diagram into components that point along these axes. Apply the equations and solve the unknown quantities. So the best way to work on the problems is to see an example. So we have an example here which is directly taken from your textbook, and it talks about how much tension must a cable withstand. I'm only giving you very simple problems to begin with. If it is used to accelerate a 1200 kg car vertically upward, so it's kind of a crane or something like that is trying to pull on a weight. So first you picturize it. How will you solve it? The first step is to read the problem. Next step is picturize. So how much tension must a cable? So a cable is lifting a car probably. Okay, so it's being lifted up, and you have to find out how much tension force is being exerted on it when it was lifted with an acceleration of 0.70 meters per second square in the upward direction, and the mass of the car is also given. So this is not a free body diagram. The next step we immediately do is draw free body diagram. In short, I will be referring to it as FBD. Okay, so the first step for a free body diagram is we just draw a dot for it. So okay, so I think I wanted to change the color. Yeah, so we pick instead of drawing the car, we draw a dot for it and we show the vectors that are acting on it. So the forces that are acting on it in the upward direction is the tension force, and the force that's acting in the downward direction is going to be the weight, that is Fg, which is equivalent to m into g. There is no horizontal force in this, no forces are acting in the x direction. There are only forces in the y direction. One is acting in the y upwards and one is acting in the y downward direction, and so no forces in the horizontal direction because it's not going in anywhere in the horizontal direction, just lifted up. So forces are only in the y direction. Now we get to write down, choose up forces as positive, up as positive, just like our axes, and down as negative. And we have to find out Ft. How much is Ft? So we apply this. This was step number 1, free body diagram. Step number 2, Newton's second law is applied in the vertical direction. So what does Newton's second law tell us? So step 2, trying to continue it from, the net forces in the y direction is equivalent to acceleration, is mass times acceleration in the y direction, and he has given us the acceleration in the y direction. We already know the acceleration in y direction is 0.70 meters per second square. If this was at rest, I would say that net forces is equivalent to 0, but since it's accelerating in the upward direction, that means there is an acceleration. What are the net forces? The net forces are formed from the upward force, which is the tension, and minus, because all downward forces are taken as negative, that's the weight, and m times ay, which is the acceleration. Ft, Fg can be written as mg, where m is the mass of the car being lifted and g is the acceleration due to gravity, is equivalent to ma. Our job here is to find Ft. So adding mg on both sides, we will get mg plus ma. You can either substitute all the values here, or you can make it a little bit easier for yourselves by taking m common and just writing it this way. So we already know the mass is given as 1200 kgs for the car, and ay, I will write this down as ay. Ay is the acceleration in y direction, which is 0.70 meters per second square, and g already you know is 9.80 meters per second square. Go ahead and pause this video and work on the substitution yourselves. So when you calculate, it will give you the answer as kg meters per second square. By the way, kg meter per second square is nothing but Newton. So you can just write newtons for this. And when we calculated it, it came out to be 1.3 into 10 raised to power 4 newtons. This is the scientific way of writing, just as you did it in your chapter 1. All these quantities are, when the quantities are big, you write them in scientific notation. So this is how we applied free body diagramming concept to these problems and tried to solve. So next we will work on a similar kind of problem, which is in the vertical direction. There is a 1400 kg bucket which is lowered vertically by a rope, in which there is 163 Newton of tension at a given instant. What is the acceleration of the bucket? Is it up or down? So what will determine whether it is up or down? We'll see. So again, I'm going to describe a scenario here. So the picture is just like it's a bucket, and it's being lifted. It's a bucket is lowered vertically. So but it has, even if it is lowered vertically, it's still connected to a rope. So the tension in the rope is always going to be in the upward direction, and the weight is going to act in the downward direction. And we have to see which direction the acceleration will be. Will the acceleration be positive or negative? If it is positive, it is in the upward direction. If the acceleration comes out negative, it will be in the downward direction. So a 14 kg bucket is lowered vertically by a rope, in which there is a 163 Newton of tension at a given instant. So mass is given 14.0 kgs. Force of tension is given as 163 newtons, and mass times gravity, that means force of gravity is mass times g. We have to find out if Fg is less than Ft, then you have to understand, will it go down or will it go up? So 163 14.0 multiplied by 9.8. Go ahead and solve it. You can pause the video while I'm also trying to go and get the number for this one. So we have 14.0 and multiplied by 9.8 comes out to be 137.2 newtons, which actually means 137 newtons. So by the way, the force in the downward direction is way less than the force in the upward direction. You can guess what will happen to will it come down or not. So step 1 was to understand what all is given here. Step 2 will be to draw free body diagram. I won't be drawing a bucket for it. I will draw a dot for the bucket, and I will represent the forces in the upward and downward direction. Watch how I have put the vector for the weight is slightly lesser, because I just found out Fg is lesser than Ft, and we are going to determine the acceleration. We don't know whether it is positive or negative, only the math is going to tell us. So step 3, apply Newton's law. Step 3, apply Newton's law, Newton's second law. that's what helps us get the acceleration. So net forces in y direction is equivalent to mass times acceleration. Again, reiterating, if I get the acceleration negative, the bucket is going downwards, and if I get the acceleration positive, it's going upwards. So the net forces are Ft upward positive, downward negative, is equivalent to mass times acceleration Ay. Our job is to find Ay, so divide both sides by m, we get Ft minus Fg divided by m is equivalent to Ay. This will help you get the Ay. So Ft is 163 newtons minus Fg we found out is 137 newtons divided by the mass, which is 14.0 kgs. So that represents my acceleration. When I solve this, I get the acceleration as Ay equivalent to 1.8 meters per second square. Since I got a positive number, the acceleration is positive, the bucket has an upward acceleration. That's the answer for the second part. So this is how we solve them. First I understood the problem. Step 1 is to understand the problem, right? Create a sketch for it and understand what is given. Step 2 is draw FBD. And third step is apply Newton's second law, and after applying and then substitute the values to get whatever it's asking us to find. So again, there is another problem. It's an elevator problem. An elevator of mass 4,850 kg is to be designed so that the maximum acceleration is 0.0680 g. By the way, this simply means it's 0.0680 multiplied by 9.8 meters per second square. So it's like kind of tricking you. So it's saying this so that you can get a little bit confused. You have to find out what are the maximum and minimum forces that the motor should exert on the supporting cable. So we have an elevator, so we say, okay, this is an elevator, and obviously we know an elevator has a cable. An elevator also has its weight. Then when it is going up, it will have an acceleration Ay. When it is coming down, it will have some other acceleration. If it's constant velocity, if it's going up at constant pace, not going with changed velocity, then acceleration will be 0. So in both cases, the free body diagram for the elevator would look like, if I go ahead and do the step 1, do FBD. So one is Ft, one is Fg, and a dot for the cable. The diagram will still look same. So that is step 1. I drew the free body diagram. Then step 2 will be to apply Newton's law. So step 2 will be applying Newton's second law, right? And Newton's second law is net force in the y direction is equivalent to mass times acceleration in the y direction. So if the elevator is going up at a certain acceleration, which was actually given to us, that acceleration Ay is 0.0680 times g, the acceleration due to gravity, which you can multiply by 9.8 to calculate it. But first, let's the scenario is same. Ft is in the upward direction, which is positive. mg, the weight is in the downward direction, is negative, is equivalent to m into ay. So you have to find the tension force, which is the maximum force if it's going up. So what are the maximum and minimum forces the motor should exert on the supporting cable? Right, so Ft will be equivalent to, you are adding mg on both sides, so you get mg plus may, and again the same way we did this, mg g plus ay. By the way, we know that ay is g plus 0.680 times g, so we can even take this g out. We can write mg out 1 plus 0.680 because I took the acceleration due to gravity out. So m is the mass, and you can go ahead and substitute the mass. Is it a negative number that's given for this? No. So you go ahead and find out. Once you substitute m as 4,580, 4,850 kgs multiplied by 9.8 and 1.0680. Oh, it's a 0 over here. I forgot to put a 0. 1.0680 because 1 plus 0.6 will be 1. So the overall answer for this comes out to be 5.08 into 10 to the power of 4 newtons. This is the maximum force. When it goes up, it exerts a maximum force. The minimum force exerted will be when it goes down. So watch the trend. Now this is going up and now going down. So when it is going down, the net forces acting on the elevator is going to be minus ay because it's coming down. So we will put it as minus y. So the scenario is it's going down, so acceleration being a vector quantity can be placed as negative. Again, the net forces Ft minus mg, which is the weight, is minus ay. But now we'll rearrange the terms again. It will be equivalent to, so adding mg on both sides, we have mg, which is when we are adding both sides, minus may, where we take m common, and g minus ay, which is equivalent to ft. So substituting the values for this, we will get, because there's a minus ay involved here, and it's going to be slightly bigger than the acceleration due to gravity because we are multiplying it by 0.680 g. We get the value of the force slightly decreased because we are subtracting the number. Okay, so it will be slightly lesser than 5.08 into 10 to the power of 4. We end up getting, after substituting the values, 4850, 9.8 and minus 0.0680 multiplied by 9.8. You could apply the same strategy and solve it just like this, but the acceleration will be slightly lesser this time, this quantity, because we are subtracting it instead of adding it. So you end up getting 4.43 into 10 to the power of 4 newtons. So this confirms that when we are going down the elevator, we weigh lesser. If I keep a spring balance, if I keep a balance weighing scale if I keep a weighing scale in the elevator and check my weight going up and down, you will find that you will weigh lesser when you're going down and you will weigh more when you're going up. So that completes this problem. And now we'll work on this is the problem that I wanted you to look at, because this is exactly the same thing that I was talking about. A woman stands on a bathroom scale in a motionless elevator, so it's not moving. When the elevator begins to move, the scale briefly reads only 0.75 of a regular weight. Calculate the acceleration of the elevator and find the direction of the elevator. So there will be two forces on the woman, her weight, and the normal force on the scale. So this is our elevator. We are not talking about elevator here. We are talking about the woman standing on the scale. So there is a normal force acting between the weight is acting in the downward direction and the normal force is acting in the upward direction. The scale is pushing on her. A free body diagram for her will look like the woman in this direction, normal force between the scale and her feet, and the weight acting downwards. When it is at rest and when it is still, there is no net force, it's equivalent to 0. But when it starts moving, choose up direction as positive as usual and use Newton's second law. So after the free body diagram, we go ahead and choose Newton's second law in the y direction, which will be equivalent to m times acceleration in the y direction. Okay, so again we do the same strategy. Fn minus mg, which is the weight in the downward direction, is m into ay. So what is the weighing scale going to weigh? That's what we are going to find out. What it said was that the normal force. Calculate when the elevator begins to move, the scale briefly reads 0.7 of a regular weight. So the normal force is what gives us the reading on the scale. So that means Fn is equivalent to 0.75 times mg. Okay, so instead of writing Fn, we write 0.75 times the mass times gravity minus mg equivalent to m into ay. Note that the m is not given, but if you notice, there is m throughout. We take m common, we get 0.75 g minus g equivalent to m times ay. And if you substitute the value of, you can even take the g out and work on it. So let's use the other page. So when we have 0.75 within the bracket, and you can take g out, minus 1 is equivalent to ay. G is 9.8. 0.7 minus 1 will come out as a negative number, which will be minus 0.75 minus 1 is, you can treat it as 1.00 or something, and it will come out to be as minus 2.5. So when you multiply it by 9.8, this comes out 9.8 times minus 0.25 is equivalent to ay, and this will give you a negative acceleration of minus 2.5 meters per second square. So if there is a negative acceleration, the person is moving down. So she is this is due to the scale going down. Then the elevator must have started to move down instead of going up from when the elevator started. In this scenario, in order to find out which direction it's going, If you got a negative value for acceleration, it's understood elevator is going down. Okay, so last problem before we end up this free body diagram for a certain style of problem. So there's a box which is weighing 770 Newton. It rests on the table. This is a very important problem actually. If you get this, you have understood most of the dynamics then. So the box weighing 77 Newton rests on the table. So that means its Fg is 77 Newtons, which is weight. And there is a normal force acting on it. And when it is resting, the normal force is equal to the same 77 Newtons because it's not going anywhere. A rope is next, we tie a rope to it. Okay, so now we have a rope attached to it, and a rope tied to the box runs vertically upwards over a pulley, and a weight is hung from the other end. So now we have a pulley over here, and the weight is hung on the other side. So this is going to either pull it, it will depend on the weight that is hanging on the other side. This is M1, this is M2. Determine the force that the table exerts on the box if the weight hanging on the other side of the pulley is 30 Newtons, 60 Newtons, and 90 Newtons. Basically, you have to find out what is that weight, that is the normal force, Fn, when you apply 30 Newtons, when you apply 60 Newtons, when you apply 90 Newtons. And by the way, the weight 77 Newtons is the weight of the block number 1. So unless and until you apply a weight greater than 77 Newtons, it's not going to get lifted from the surface. So normal force ceases, Fn ceases to exist when an object loses contact with surface. If the object is not touching the surface, it's not touching the surface. If it's in air, it will not have Fn anymore. So keeping that cue in mind, let's go ahead and solve this one. So the free body diagram, for example, for the box, there will be two free body diagrams. So this is the box which is on the table, and there are several forces acting on it. One is the normal force, and one is also the tension force because it's connected to the rope. So there is tension force also, and there is M1G. So three forces: normal force, tensile force, and M1G on mass 1. Then there is mass 2, which is on the other side. It has only two forces. One is the tension force in the rope, and the weight M2G, which is in the downward direction. So it's the same scenario that we were talking about behind, since now it's on the other slide. Then it's running through a pulley. So in this direction we have Ft, and in this direction we have force of tension, and in this direction we have M2G, because this is M2 and this is my M1, and we have M1G here. And apart from that, there's a normal force acting on this because it's sitting on a table. So scenario 1, it says if the weight of the hanging weight is less than the weight of the box, the object will not move and the tension will be the same as the weight of the hanging weight. So Ft will be simply equal to M1G, right? And the acceleration of the box will also be 0. So acceleration will be 0 because it says the weight on the other side is 30 newtons. So look at the question here. 30 newtons is less than, so 30 newtons is less than, is way less than our 77 newtons. So not moving at all. So we can apply, so if I apply the forces, so it will not have acceleration, but it still has, we can still do the net force in the y direction is equivalent to net force, or so let's write in the same format. Fy is equivalent to m into acceleration in y direction, but we already know there's no acceleration, so we treat it as 0 and we write it equivalent to 0. Okay, so now what are the net forces? All upward forces positive. There are 3 upward forces. Fn, there is tension force, but m1g is in the downward direction, equivalent to 0. Okay, so our job is to find what is the scale reading. So that means we have to find Fn, which will be equivalent to m1g plus force of tension. So force of tension here is going to be same as m2g, so which is 30 newtons. So 30 newtons, oh sorry, this is minus, so m1g is given as 77.0 newtons minus 30 newtons. That means the scale will read 47 newtons. Then we go ahead and look at B. If I change this, the tension force on the other side to 60 newtons, we simply modify this equation without doing all these steps. We know what we are doing now. The normal force will then be equivalent to m1g minus ft again, but m1g is the same 77 newtons, but ft has changed to 60 newtons, and the normal force is now little decreased because we have started increasing the weight on the other side. So that comes out to be 17.0 newtons. Now for part C, now the scenario is different. What will happen to normal force if we have Fn is equivalent to m1g, and now we don't have, since the hanging weight has more weight than the box on the cable, the box on the table will be lifted off. So there is no way to calculate it now that it has lost contact with the surface. Fn will be 0. Although you would be tempted to put this as you would want to replace this as 90, but it's a conceptual fact. When the object is not in contact with the surface, its normal force is 0. So we'll meet in the next, we'll talk about frictional forces, and this ends today's slide.